So guys, welcome to this another video, and this is about computing determinant. So in this video we'll basically try to evaluate this determinant in 5 different ways. They're eventually connected to this same way that's in the first label, right? Basically this is the major way to find determinant, but all of them will be different, like they will not be same anyways. So yeah, so let's start with label 1, which is the cofactor expansion, and this is the one that all of us learn in the high school or in the college. So basically this is a regular method, and in this method how we find determinant is okay. So in this method, so let's say I want to find, and determinant is also represented by this modulus symbol, right? If I write it like this, then I think you need to understand that I actually mean the determinant. Okay, now the how the cofactor method expansion method works. So the determinant of 1 2 3 1 1 3 2 1 2, right? Okay, now how this works is, first of all, we will assign signs with the matrix. Basically this is a check, the sign will be in checkerboard pattern, this place has plus sign, this has minus sign, this has plus sign, minus plus minus sign, again plus minus plus sign. We will assign those, right? And now based on those signs we will try to expand this determinant in the following way. So first of all, we will just have this first number. Okay, I can do it with any row, doesn't matter. Okay, let me do it first row for now. So I will start with the first element of first row, 1, right? And this has plus sign. And now with this 1, what I will do is I will just exclude the rows and column where there's 1, and then find the determinant of the remaining the remaining this 2 by 2 matrix, right? And yeah, determinant of 1 3 1 2. Okay, so now again, now after this I go to 2, but 2 has negative sign, right? And then I multiply this 2 with, I'll just exclude the rows and column where there's 2 and find determinant of this 2 by 2 matrix, 1 3 2 2. 1 3 2 2. Determinant of 1 3 2 2. Now again, now this 3 has plus sign. I will multiply this 3 with determinant of the matrix excluding the row and column where 3 is. So 1 1 2 1. 1 1 1 2 1. Okay, and this works not just for 3 by 3 matrix, for any, even for 4 by 4, 5 by 5. What you need to do is just go over the top row, right, using the plus minus sign. And always what just that you need to do is just exclude the row and column containing that number, and for 4 by 4 you will basically get a 3 by 3 matrix over here, right? And now find determinant of this 3 by 3 matrix. Of course the work will be tedious, but yeah, the way is same. Now evaluate this. So this will just be, now 1 for 2 by 2 it's easy, right? For 2 by 2 determinant is just, for ABC determinant is just AD minus BC, right? So yeah, so it's just AD minus BC, so it will be 1 into 2 minus 1 into 3, negative 2 times, this is just 1 into 2 minus 2 into 3, plus 3 times 1 into 1 minus 2 into 1. Now this is 2 minus 3 will just be negative 1 minus 2 times, this is just 2 minus 6 is negative 4, plus 3 times 1 minus 2 is negative 1. So this is negative 1 plus 8, negative 3, 8 minus 4, so the determinant is 4. And this is how we find determinant using the regular method. That means the method where we expand it using the cofactor, right? Okay, so now next one is fairly simple, say fairly simpler and shorter than this one, which is Sarah's rule, and this rule this rule is basically like based on the same result, but like from the result, like you will like seeing it in a different way, like Pyre format. Like I mean, the French mathematician Sarres came up with this rule. Yeah, so this rule basically works on the same principle of cofactor expansion. So yeah, rule of Sarres. So let me show you how this works. Rule of Sarres. So again, let me we are finding the determinant of 1 1 2 1 1 3 3 2. So 1 1 2 2 1 1 3 3 2, right? 1 1 2 2 1 1 3 3 2. Yeah. Okay, now let's find the determinant. Okay, in Sarres rule, how we what we do is we first of all write this as it is. I mean, in this one, first of all, we just write the all three columns, and then again we write the first column and then second column, right? Now, uh, we try to mark these diagonals. Basically, these lines are just parallel, and this starts from the first element and just like goes one step down, right down, right. This also goes down, right, down, right, down, right, down, right. So we mark these lines. We mark all the set of lines from from bottom as well. This set of lines, right? Now what we do is we multiply all the elements in red line, right? So there will be three such products, and we add the products. So basically, what we do is now 1 into 1 into 1 into 2. So this is in first red line, plus 2 into 3 into 2, which is in second red line, plus 3 into 1 into 1, which is in third red line. We add this and we subtract this with allos. So first of all, 2 into 1 into 3 in first allo line, plus 1 into 3 into 1 in second allo line, plus 2 into 1 into 2 in third allo line. Now this is just 2 plus 12 plus 3 minus 6 plus 3 plus 4. So this is just 17 minus 13, which is 4. So we got the same determinant, which is 4. Now if you are wondering how this works, now to verify it for yourself, just take a general determinant like A, B, C, D, E, F, G, H, I and try to see the result you get from this, right? And I mean, try to see the result, right? And now like try to find determinant from this process and try to see how you can take the result from this process to the one that you achieve over here. And yeah, like and you will get the idea. Just try taking determinant of general matrix and you will of like just variables, and then you will get the idea. Now let's go to level 3. This is rule of Sarres. This is regular method. Now level 3 is row reduction to triangular matrix. Now before I go to this one, I will also introduce you with some tools of um, row operation, right? Row reduction to triangular matrix. Now first of all, what is row operation? In using row operation, why do we want to transform the matrix given matrix to triangular matrix? Now I just need to give you some background before I go to the process, right? Now first of all, you should know that what a triangular matrix is. Like triangular matrix is basically, let's say this is a main diagonal. Let's say this is A11, this is A22, this is A33, right? And this is second row first column, third row first column, third row second column, 0 0 0. Now if there's such matrix such that every element above the main diagonal are all 0, then this is called upper triangular matrix. Sorry, I mean there are elements in the lower side, so this is called lower triangular matrix, right? And there can be matrix like this as well, A11, A22, A33. Now this is first row, second column, first row, third column, second row, third column, 0, 0, 0. Now for this matrix, since there are elements above the main diagonal and elements below the main diagonal, so this is our basically the main diagonal, right? And below the main diagonal all are 0, and there are elements above the main diagonal, so this is called upper triangular matrix. Upper triangular matrix. Now, good thing about this triangular matrix is that, but for both like low and upper triangular matrix, if you try to evaluate the determinant, let's say if you try to evaluate determinant A11 0 0, A21 A22 0, A31, not just for 3 by 3, like this one is applicable to all of like matrix of any order. Okay, like this Sarus rule is only for 3 by 3 matrix. I forgot to say that it's only for 3 by 3 matrix, and except Sarus rule, all others are for like matrix of any order. Now we were there, we were here. Now, good thing about determinant of triangular matrix is that if you try to evaluate this will just be A11 times, right? Now, from the rule 1, we know that this will be A11 times, again, determinant of this thing is just A22, A33 minus 0, right? And then minus, there's 0 times something which is just be 0, right? Again, there's plus 0 times something which is just be 0, right? So you see that for a triangular matrix, the determinant will just be the product of the diagonal elements. So this is a powerful result for a triangular matrix. For a triangular matrix M, determinant of M is just product of diagonal elements, main diagonal elements. And yeah, so though we like needed the first way for like to prove this thing, but yeah, now after we know this, then like we can like find determinant in a fairly similar way. Okay, now I guess you got this idea, right? For a triangular matrix, determinant is just the product of diagonal elements. Now let's go to row reduction. So basically, like there's something known as row operation in matrix, like which I will tell you. Just a slight introduction. And there are 3 row operations, right? Basically, there are 3 row operations in matrix. Let's say for a matrix A11, A22, A33. This is first row, second column, first row, third column, second row, second column, second row, first column, third row, first column, third row, second column. Now the first row operation is swapping rows, right? Swapping rows. So that means if I like make a row operation, let's say this is our row 1, row 2, row 3, right? Okay, now if I swap like row 2 with row 3, our matrix will just become A11, A12, A13. Now this will be A31, A32, A33, and then okay, let me check if sound is recorded or not. Oh yeah, good. Okay, and then A21, okay, A21, A22. Oh wait, there should be A23. I'm sorry, and A23, right? Okay, so this is one of the row operations where we swap the rows. Now next row operation is scaling a row. There are just 3 row operations, so like don't worry. Now scaling rows, that means let's say if I in this very matrix, in this matrix, if I make that row 2 to be k times row 2, so this is like is about scaling the row. And now the matrix will become A11, A12, A13. Now row 2 will become k times A21, k times A22, k times A23, right? And then A31, A32, A33. So this is our second row operation on matrix. And the third row operation is, I will tell you the reason you need to know this, but for now, just know that yeah, such things are there. And the third one is adding a scaled row, adding a scaled row to another row, to another row. So that means, like, now how this row operation works is, let's say if I say that row 2 is row 2 plus k times row 1, where k can be any integer. So yeah, this is called, like, this is our third row operation. Now if I do this row operation, what will happen is, in row 2 I will have row 2 plus k times row 1. So that means row 1 will be as it is, right? But row 2 will be row 2 plus k times, now only this corresponding element will be added. These two will not be added to this one, okay? So this will just be k times a11. Now over here, a22 is just row 2 element plus k times a12, and this is a23 plus k times a13. So this is called this is the third row operation, right? And yeah, okay. Now what we will try to do is, okay, now using this row operations, what we will try to do is, for the given matrix, let's say for, in this case, our given matrix is 1 1 2 2 1 1 3 3 2, right? 1 1 2 2 1 1 3 3 2 3 3 2. Now what we will do is, first of all, okay, so what we will do is, first of all, we'll just say that the determinant of this matrix is D, right? And like, we will go on like doing row operations on this matrix. We'll go on doing row operations on this matrix such that we eventually make this matrix a triangular matrix. So we will go on doing row operations so as to make this matrix triangular matrix. And once it becomes triangular matrix, it's easy to calculate determinant, right? Just take the product of diagonal elements, right? Yeah. And so yeah, once it becomes like triangular matrix, we will be able to find out, right? Now, like when we are doing, like, let's say specific row operations, like let's say if you do a row operation R, I don't know, like let's say R, if I do R, then for every row operations, like, we can also find out how that changes determinant, right? So there's some way I will tell. So for every row operation, we will also be able to predict how the determinant will change, right? Now going the, like, when we are doing row operation, we will also store how D will be changing. And finally, let's say over here we get D times some number n, right? And our matrix has now finally transformed to triangular matrix, right? Let's say A B C D E F 0 0 0. So yeah, we did some row operations, we know how D will transform, and like finally this has gone to a triangular matrix, right? And now D has gone to D times n. So now in this case, now we know that D times n will just be, now we can find determinant ABC, right? And we can find the original determinant too, which will be ABC by n. So this is how we will try to find the determinant. You get the idea? Right. Now the only thing that's remaining is, how do we find that like for a given row operation, how much will the determinant be scaled, right? Like how will determinant change with the row operation? Now we need to know that, right? Okay. So now I will tell you like how will determinant change with these three row operations. And if we know that, then we will be done. Then it will be like we are almost done. Then we can easily do it. Now let us discuss how these row operations change the determinant. Okay, now first of all about swapping the rows. Now about this you can experimentally verify, or you can just go with the formula and then verify it. Now whenever you swap two rows, like let's say if the determinant of now I'll just write a shortcut, A B C D, E, F, G, H, I. If its determinant was, let's say, D, now if you swap, let's say, second and third row, guys, but notice that swapping rows means swapping immediate rows, okay? Like I'm discussing about that. No, not a, you can, no, not about directly swapping the first and third row, swapping immediate two rows. So if you like swap immediate two rows, and if you are wondering like am I not allowed swapping the first and third row, right? So yeah, you are allowed to swap that too, but that's not a row operation. Okay, so yeah, if you swap like immediate two rows, let's say if I swap A, B, C, G, H, I, D, E, F, the determinant will just be negative. Okay, will just multiply by negative 1. You can verify this by yourself. Now next is scaling. Next is scaling a row. Scaling a row. Now let's say a determinant of A, B, C, D, E, F, G, H, I was D. Now let's say you scale the second row by K. If you scaled one of the row by K, right, then our determinant will just be scaled by K. Our determinant will also just be scaled by K. You can also verify this for yourself. It's not that hard. Now the third one is okay. Now the third one is about like adding a scaled row, right? Adding a scaled row to another row. Scaled row to another row. Now let's say if I have A, B, C, D, E, F, G, H, I, whose determinant is D, right? Now if you consider this one, if you just scale second row and add it first one, A plus KD, B plus KE, C plus KF, right? D, E, F, G, H, I. Now surprisingly its determinant will also be D, and you can verify this from the fact that you can basically divide this determinant as the sum of these two determinants, KD, KE, KF, DEF, GHI, and now the fact that now second determinant is just linearly dependent, so its determinant will just be 0 plus, and this was D, so this will just be D. So you should get these three ideas. So for the third row operation, determinant remains unchanged. For scaling a row, determinant will also be scaled by that number. And for swapping two immediate rows, determinant will be negative. And like if you swap non-immediate rows, let's say first row and third row, non-immediate rows, determinant remains unchanged. Determinant remains unchanged. You can verify this for yourself, guys, or you can also like find some rigorous algebraic proofs for yourself. Or you can, or if you know that this determinant actually represents volume of three made by three vectors, then that can also help you interpret, right? Visual interpretations are always better. So yeah, you can try interpreting them. Okay, now we know that, guys. Yeah, now after we know that how these three row operations like affect determinant, now we are good to go. The first one makes it negative, the scaling scales determinant, and scaling and adding makes like determinant is unchanged. Okay, so now let's go over here. Now in this case we want to make it triangular matrix, right? So okay, so first of all what we can do is, I guess you guys know that this is row 1, this is row 2, this is row 3, right? Okay, now first of all, if I want to make it triangular, I will just try to make these three elements 0. Okay, so for that what I can do is, first of all I will just do row 2 as row 2 minus row 1. This is our third operation, and like I guess you guys know that in this operation determinant remains unchanged, right? So again still like our new matrix formed will have the determinant, the new matrix formed will be, so if I do row 2 minus row 1, 1 minus 1 is 0, 1 minus 2 is negative 1, 3 minus 3 is 0, right? And 2 1 2, and its determinant remains unchanged, so it will still be D. Okay. Now I want to make this two zeros. So what I can do is I can do row 3 as row 3 minus 2 times row 1, right? This is again the third row operation. If I do this, our third row will now be, so 1 2 3 0 negative 1 0. Now 2 minus 1 times 2 is just 2 minus 2 0. 1 minus 2 times 2, that means 1 minus 4, which is negative 3. And 2 minus 3 times 2, 2 minus 6 is negative 4. Okay, and this again is just D, because third row operation doesn't change the determinant. Now I need to make this negative 3 0, right? If I'm able to do that, then this will be a triangular matrix. So what I can do is, let's say row 3 be row 3 minus 3 times row 2, because if I do that, this negative 3 will just be negative 3 minus 3 times negative 1, right? Because there's negative 1 row 2. So this is just negative 3 plus 3, which is 0. So that will become 0. So that's why I did this. So if I do this, row 3 as row 3 minus 3 times row 2, again for this third row operation, determinant remains unchanged, and determinant now for this matrix will change to 1 2 3 0 negative 1 0. Now 0 minus 3 times 0 is 0. Negative 3 minus 3 times negative 1 is negative 3 plus 3, so 0. And negative 4 minus 3 times 0 is just negative 4 again. So you see that, right? Okay. Now we have transformed this to a triangular matrix. So now we can calculate this by just multiplying diagonal elements, which is 1, negative 1, negative 4, which is again just 4. So over here there's no such n times D. If it was there, we just would have taken n to other side and divided the 4. But since there is no such thing, so D is just 4. So yeah, D, and basically we had told that D is determinant of the original matrix, so its determinant is just 4, which is exactly what we have got in both the Sarus rule as well as regular method, right? Now we are good to go to level 4. Level 4 is LU decomposition. It sounds hard, but it's actually easy. This LU stands for lower triangular, upper triangular decomposition. Okay. Level 4, which is lower triangular, upper triangular decomposition. Okay, and we have the matrix that we want to compute. Determinant is 1 1 2 2 1 1, and this is 3 3 2, right? 3 3 2. Okay. Now first of all, we just need to know a theorem, right? And yeah, just try to understand theorem first, and then we'll go into this thing. Well, what the theorem says is, for any non-singular matrix M can be written as a product of a lower triangular matrix L and upper triangular matrix M. That means, let's say for any matrix A11, A22, A33, let's say M is this matrix and determinant of M is not 0. That means if determinant of M is not 0, then it's non-singular, right? Only if determinant is 0, then the matrix is singular. So for a matrix, let's say first to second column, A13, A23, A21, A31, A32. Okay, for this matrix, this can be written as a product of like a lower triangular matrix. Let's say A, B, C, D, E, F, 0, 0, 0, and upper triangular matrix P, Q, R, S, T, U, 0, 0, 0. So this is the theorem. This theorem says that any matrix M can be like written as a product of a lower triangular and upper triangular matrix if M is non-singular. Now, how this can be helpful to us? So this can be helpful to us because instead of like let's say if we get a complicated, let's say for 5 matrix, we'll just try to decompose that matrix into two matrices which are lower triangular and upper triangular, right? And once we do that, now now, since we know that, like let's say if I want to find, let's say this matrix I name it as A, and I name this as B, right? And this matrix is M. Now, if I want to find determinant of M, what I can do is, since I know that M is A and B, right? And now, since like a determinant can be distributed, I mean, no, not distributed. What do I say it? Anyways, since I can write it like this, I can just break it into two parts. So yeah, now so I know the determinant of this first triangular matrix is just A times D times F, and second is just P times Q times R. So defining determinant of M becomes easier. You see that because upper triangular, lower triangular matrix, their determinant is just product of diagonal elements. So yeah, if you can make this breakdown, finding determinant, it becomes so easier. So this is how this is helpful. And in this video, we'll try to break this 3 by 3 matrix to two upper triangular, lower triangular matrices, and it will not be that hard actually. We just need to assume that that exists, and we need to solve a few equations, and we will get the elements of upper triangular and lower triangular matrix. Okay, now let's get started. So we have this matrix 1 1 2 2 1 1 3 3 2, right? And we want to break this into a lower triangular matrix. Let's A11, A21, A31, A22, A32, A33 times 0 0 0 multiplied with let's say B11, B21, B31, B22, B32, B33. Oh no, one of them is lower triangular, other is upper triangular. I'm sorry, I made both of them lower triangular. So B11, B12, B13, B22, B23, B33, 0, 0. Wait. I'll charge it. Wait, guys. Okay. Then B32, right? Okay. Yeah. Now, no, wait. This should be 0 actually. Okay, I want to break it like this, right? Now I'll just make a few equations by multiplying these lower triangular upper triangular matrices, and we'll solve them. 2 1 1 3 3 2. If I multiply, I will just get. So first of all, I will multiply this first row with first column. So A11 B11, right? A11 B11. Now if I multiply first row with second column, again A11 B12, right? A11 B12. If I multiply first row with third column, A11 B13, right? A11 B13. If I multiply second row with first column, A21 B11, right? A21 B11. If I multiply second row with second column, A21 B12, A22 B22. A21 B12, A22 B22. If I multiply second row, if I multiply second row with third column, A21 B13, A22 B23. Okay, so this will be A21 B13 plus A22 B23. Okay, now Now, yeah. Now if I multiply third row with first column, A31 B11, right? A31 B11. If I multiply third row with second column, A31 B12, A32 B22. Yeah. A31 B12, A32 B22. Now if I multiply right over here with A11 B13, right? A11 B13. Now if I multiply third row with third column, oh, that will be long. A31 B13 plus A32 B23 plus A33 B33, right? Okay. Now guys, now what we will do is we will just try to compare the corresponding elements in two matrices, right? So first of all, corresponding to A11 B11, A11 B11, we have over here the first element is 1 compared to A11 B12, the second element is 2 compared to A11 B13, the third element is 3 compared to A21 B11, this is 1, A21 B12 plus A22 B22, this is 1, and then A21 B13 plus A22 B23, this is 3, and then A31 B11 2, A31 B12 plus A32 B22 1, and then A31 B13 plus A32 B23 plus A33 B33 is just 2, right? So 1 2 3 1 1 3 2 1 2. Okay. Now guys, this looks good, but the only problem is there are 9 equations, but there are 1 2 3 4 5 6 7 8 9 10 11 12 variables, right? So there are 9 equations, 12 variables, and usually we need to have equal number of equations and variables to solve, right? So yeah, definitely this will have a lot of solutions. This will not really have exact number of solutions, but will have a lot, right? So therefore we have to make some restrictions. So what we will do is, if we just say that these three elements are just 1 1 1, right? If we just make the diagonal elements of triangular matrix to be 1, now we have exactly 9 variables, 9 equations, right? And now we'll be able to solve it. So that's what we do. So we just say that A11 A22 A33 are just 1 1 1. We will say that, and yeah, A11 is 1, A22 is 1, A33 is 1. Okay, now if we do that, I can find B11 from here, which will just be 1, right? I can find B12 from here, which will just be 2, right? And I can find B13 from here, which will just be 3, right? Now I can find, okay, B11 is 1, so A21 is also 1, right? And now, okay, B11 is 1 from here, I guess you know that, just in case here. Now again, B11 is 1 from here, so I can substitute that over here. So A31 will be 2, right? Now, okay, so I have A22 is 1, B12 is 2. I know A21 as well, I know B12 as well, I know A22 as well, so I can find B22, right? So this is a21 is just 1, b12 is just 2 from here, plus a22 is just 1 times b22 is equals to 1. So b22 is equals to 1 minus 2. So b22 is equals to negative 1. So we got b22 as well. Now I can try to solve this, I guess. I have a31 already, b12 already. I don't have a32, but I have b22 from here, right? So I can solve it. This is 2 times b12 is 2 plus a32 times b22 is negative 1, which is 1. So a32 negative a32 is equals to 1 minus 4. Negative a32 is equals to negative 3. So a32 is equals to 3. So we have a32 as well. Now I have a21, I have b13, I have a22 which is 1. Now I can find b23, right? So yeah, a21 is 1, b13 is 3, plus a22 is 1. I need to find b23 is equals to 3. So b23 is equals to just 3 minus 3. So b23 is equals to just 0. Now a31 is 2, b13 is 3, plus a32. Yeah, it's 3, b23 0, plus a33, it's just 1 times b33, which is 2. So this is 6 plus b33 is just 2. So b33 is just negative 4. So it's just negative 4. So we have all these numbers, right? So we solve for all 9 variables. Basically we have over here all 9 variables now, right? 1 2 3 4 5 6, sorry, all 12 variables, right? Yeah. Now if we have all these 12 variables, now I can write this matrix 1 1 2 2 1 1 3 3 2 as a product of two upper triangle and lower triangle matrices. So a11, and guys, also know that I don't really need all of these, because I know that its determinant is just like the product of diagonal elements of the first lower triangular matrices times diagonal elements of the second upper triangular matrices, right? I don't need all of them. Now since I know that this a11, a22, a33, they will just be 1 1 1, and now the rest b11, b22, b33, this b11 will just be 1, b22 will just be negative 1, b33 will just be negative 4. So now you see that this is 4, right? So I don't even need to do a lot of things. I can just use this fact directly, that it's just ADF times PQR. So this is our ADF, this is our PQR, and this is how I can find it. I don't need to, even though like let me write it for now, guys. This system is being heated a lot, so let me uncharge it for some minute and then I will again charge it. This connecting port is heated a lot. Okay. Now, so yeah, now let me just let me write it for the sake of completion. A11 is just so this is just 1 1 1, and then a21 is just 1, a31 is 2, a32 is 3, this is 0 0 0 times, and b11 it's just 1, b12 just 2, b13 just 3, b22 just negative 1, b23 just 0, b33 just negative 4, and then 0 0 0. Yeah, so this is it. And now if we try to compute the determinant of this matrix 1 1 2 2 1 1 3 3 2, this will just be determinant of both of this matrix, and its determinant of both in the determinant of the first matrix times the determinant of the second matrix, right? 1 0, I know that, 1 0 0 2 negative 1 0 3 0 4 negative 4, and determinant of the triangle matrix is just product of diagonals. So 1 into 1 into 1 times, and this is just 1 and negative 1 negative 4. So yeah, so this is 1 times 4, that's just 4, and that's what we have been always getting, right? 4 in average step 4. But here also we got 4. This is our level 4. Yeah, we always got 4. Now the last one is a really nice one, the eigenvalues diagonalization. Guys, if you don't know about the eigenvalues, I recommend you to go to my just previous video where I found the cosine of a matrix. In that, I have like really explained what eigenvalues and eigenvectors are from very basic, right? And I don't think I'm going to do that again in this video. I'll just put that video in the like comment section. Yeah. So yeah, or you can just check the video just before this one, or like there's a playlist about matrix algebra or algebra, you can find it there as well. So yeah, so I will just assume that you know what eigenvalues and eigenvectors are for level 5. Okay, so level 5 is eigenvalues and diagonalization. Okay, now again the matrix is just 1 1 2 2 1 1 3 3 2. Now if you know about the eigenvectors and eigenvalues, then you will know that there are three such special eigenvectors for a 3 by 3 matrix. For a 3 by 3 matrix, there will be three vectors. Like let's say a1 b1 a1 b1 c1, a1 a2 b2 c2, a3 b3 c3. There are three such special eigenvectors for a 3 by 3 matrix, and there will be three corresponding to each of these vectors. There will be three such eigenvalues: lambda 1, lambda 2, lambda 3, right? Now these are the eigenvalues, and these are the eigenvectors. Now if you know this fact, now you might also know that we call the matrix of eigenvectors by P. We denote the matrix of eigenvectors by P, right? So P will just be A1 B1 C1, A2 B2 C2, A3 B3 C3, and we denote the matrix of eigenvalues by D. So D basically refers to a diagonal matrix, and the reason it's called diagonal is only diagonal elements will be there in this matrix, rest of them will be 0. So this is how diagonal matrix is, right? And the special thing about this P and D matrix is that basically if this is matrix A and this P is the eigenvectors of this very matrix M, and D is the like diagonal like matrix for this very matrix M, then M will just be equals to P D P inverse. So yeah, this is the special thing about the P and D matrix, right? So basically if you know about transformation, this is just about like transforming into the like space of transforming into the like space of the eigenvalues, and then scaling over there and then coming back, something like that. But yeah, for now we don't need to go into the details. Yeah, so just know that every matrix M can be written as like P D P inverse, where P is the like matrix of eigenvectors and D is diagonal matrix of eigenvalues. Okay, now the helpfulness of knowing this fact is that now if you know this fact, now let's say if I want to find determinant of matrix M, this will just be determinant of this whole thing, right? And this will just be determinant of P, determinant of D, determinant of P inverse, right? Determinant of P, let it be determinant of P as it is. Now since like D, this diagonal matrix is also a triangular matrix, right? Both lower triangular and upper triangular. You can clearly see that, right? And if it's a triangular matrix, the determinant will just be the product of diagonals. So this will just be lambda 1 times lambda 2 times lambda 3, right? And you should know the determinant of a P inverse is just 1 by determinant of P, right? If you know that, you can see that these will just cancel out, and this thing will just be product of the eigen values. Now from here from here we get an interesting formula that for a matrix, if you want to find determinant of a matrix, this will just be the product of eigenvalues. This is actually a really interesting formula, that it's just a product of eigenvalues, right? Now we just need to find eigenvalues. Now, I didn't tell you earlier, but now how to find eigenvalues is dependent on its definition. That basically eigenvectors are such vectors. Like for every matrix M, there are such vectors B, so that if you multiply that matrix with this vector, this will just be scaled. This will just be scaled by some constant. So yeah, M is a matrix, but lambda is a constant. So this is the definition of eigenvectors and eigenvalues. So this is the definition that governs them. Now, now if you try to, now using this definition, we will try to find lambda, right? So we'll just manipulate this in some ways. So I can basically take this to other side, right, and let that be zero. Now, now what I will do is I can just take b common, right? And if I do that, over here I will just have m minus lambda, right? Now this is a man, this is a number, right? And that's not really push. We cannot do that. We cannot subtract a number from matrix, right? So what I can just do is I can just introduce one in matrix form, which is just I, right? And say that this is equals to zero. Now these eigenvectors will never be a zero vector, so this will not never be zero. And also this matrix will also be non-zero, because there's this lambda times I, and lambdas are non-zero, so definitely they cannot be zero, right? Now if we know that these none of these two are zero, but still their product is zero, right? Now since we know that both of them are non-zero, what I can do is, there is certain condition, like in which even though we have two non-zero matrices, when multiplied can give zero. So I'm trying to derive that condition. So for that, what I will do is, so I will first assume that this m minus lambda I, this matrix has inverse. I will assume that this has inverse, right? And if I do that is assumption, if I do that assumption, I can take it to other side, and then yeah, I can multiply this inverse with now this is the not zero, this is actually zero, like zero matrix, right? Because we are dealing with matrix. Now we can see that this vector will just be zero. If I assume that m minus lambda has inverse, vector will just be zero, but we clearly know that the eigenvectors will not be zero. So this is the contradiction, and that means my assumption has failed, that m minus lambda I cannot have inverse in this case for the product to be zero. So if m minus lambda I cannot have inverse, that directly implies that the determinant of m minus lambda I should be zero, because only if determinant is zero, then it doesn't have inverse, right? Because now it's a singular matrix. I guess you know that. Now yeah, this condition will help us find the lambdas. And if I find the lambda, because basically these lambdas are our eigenvalues, and we will just find product. So there will be three different values of lambda: lambda 1, lambda 2, lambda 3. Now our matrix is 1 1 2 2 1 1 3 3 2 minus lambda times I, basically means just the unit matrix 1 0 0 0 1 0 0 0 1, right? And we know that this needs to be 0. And yeah, now I can just like multiply by lambda and then subtract two matrices. So this is 1 minus lambda 2 3 0. This will again be 1 minus lambda 3 2 1 2 minus lambda, right? Now I guess you know how to find determinants using the way that we first discussed. Yeah, we already discussed how to find the determinant now. So guys, this is indirectly using the same way that we discussed in the first method. So yeah, you might be feeling like, why did you do this? But yeah, like this is just good to. Okay, now minus lambda times, if I find product of these two, this will just be 2 minus 3 lambda plus lambda square, right? Now negative 2 times, this will just be negative, is it negative 6? Oh wait, this is not 0. This is not 0. This is 1, right? That's 1, right? Yeah. Okay. So yeah, so if that's 1, Now negative 2 times, this will be 2 minus lambda minus 6, plus 3 times, this will be 1 minus 2 plus lambda, right? 1 minus 2 plus lambda, no, not lambda, 1 1 minus 2 plus 2 lambda, right? Yeah, that will be 0. Now this will just be 2 minus 3 lambda plus lambda square minus 2 lambda. Guys, I think I'm wrong. 1 minus lambda times 2 minus 3 lambda plus lambda square. Yeah, over here I forgot to do negative 3. I forgot to do negative 3, guys. So yeah, there was a problem. Definitely there was a problem. Okay, now this will just be 1 minus lambda times, so this will just be lambda square minus 3 lambda minus 1, right? Okay, now in this, then this 2 times, this will be minus lambda minus 4, and this plus 3 times 2 lambda minus 1, this should be equals to 0. Now this is lambda square minus 3 lambda minus 1 minus lambda cube plus 3 lambda square plus lambda, right, plus 2 lambda plus 8 plus 6 lambda minus 3 is equals to 0. Now there's 1 minus lambda cube, right, and there's 4 lambda square, and there's 6 7 8 9, so plus 6 lambda, and 8 plus 4 is equals to, wow, where did this happen here? It's the first time this happened. This side. I had never experienced this, guys. I had never. Okay. Oh wow, wow! It was able to reissue. That's nice. Previously in laptop also this used to happen, and it did not use the register. But yeah, this one is good. Okay, so yeah, plus this is 8 minus 3 5 minus 1, yeah, 4 plus 4 is equals to 0, right? Now I just need to solve this one. Minus, okay, but guys, I don't even need to solve this equation, right? The reason I don't need to solve is, now first as equations, I know that it's a like cubic equation, so it will have three different solutions, right? I mean, they can be same as well, doesn't matter. They can be complex as well, doesn't matter. But yeah, even though they might be same or complex, they, like this will basically have three different solutions. And yeah, now there's Beta's formula. There's Beta's formula, which says that, like, for such an equation, let's say a lambda cube plus b lambda square plus c lambda plus d is equals to 0. The Beta's formula says that if the three solutions be lambda 1, lambda 2, lambda 3, then the sum of the solutions will just be negative b by a. The solutions taken 2 at a time will just be c by a, and solutions taken 3 at a time, their product will just be negative d by a. Now in this case, since we just want the product, right, we just want the product, so lambda 1 lambda 2 lambda 3 will just be negative d by a, and d is negative 4, so negative of negative 4, a is just 1, so their product is just 4. And yeah, therefore our determinant of this matrix that we have, okay, now we know that the, like, the product of the eigenvalues for this matrix is just 4, right? So that means this, its determinant is just 4. And yeah, that's how we calculate by this method. So these are the 5 levels of finding determinant. The first one, the cofactor expansion, the normal one. Second one, the rule of Saras. Third one is row reduction triangular matrix, and just recording these steps, like how determinant changes. Fourth one was lower, like decomposing into a product of lower triangular, upper triangular matrices. And the last one was eigenvalues and diagonalization. So yeah, this was it, guys, and this can actually be helpful in cases where you actually know the lambdas, right? So it can be helpful in those cases. because there are ways like Fourier, discrete Fourier transform that can help us find lambdas, and we also use this for like let's some sort of cyclic matrices, right? So yeah, there are cases, all of them can be helpful. So definitely it's better to know all of them. And yeah, let me know if you have any others too. And yeah, it's definitely good to share with all of us. You can let us know in the comment section. So that's it for today, guys, and I look forward to seeing you in the upcoming videos too.